Hello, am I audible, Pratap? Pratap, if you are able to hear me, unmute yourself.
Yes, sir.
Okay.
Yes, sir.
So everybody is able to hear me?
Yes, sir. Yes, sir.
Deepa, Anbarasi, Anshul, I hope you are able to hear me. If yes, then confirm it by saying a yes.
Yes, sir.
Okay. So, as you are seeing on the board, today we are going to start learning a new chapter. The chapter name is Kinetic Theory of Gases. Yes, it is a continuation of what we are learning from the previous chapters. That is, if you see, when we start talking about thermal properties of matter, from there this part started, where we are going to learn about heat and its effect. So first we learned about thermal properties of matter, where we learned about what is thermometry and calorimetry. In thermometry, we learned about the measurement of heat, measurement of temperature actually, and in calorimetry, we learned about measurement of heat. We learned about how to measure a heat if temperature is changing and state is not changing. We learned about how to measure the heat if state is changing and temperature is not changing. So one thing is called as latent heat, which is equal to ml. Q is equal to ml, mlf or mlv. And if the temperature is changing and state is not changing, that heat energy is found by using the formula Q is equal to mc delta T. Sorry. But after that, we have learned in the chapter about Newton's law of cooling, conduction, convection, radiation, and all these things. In thermodynamics, we continued learning those things, and we learned mainly about what is system, what is surrounding, thermodynamic variables, thermal equilibrium, thermodynamic equilibrium, and we learned about zeroth law of thermodynamics, where it just told us that two bodies, if they are in thermal equilibrium with third body, then they are also in thermal equilibrium with each other. We learned about first law of thermodynamics, where we learned that whatever heat energy is applied to a system, it is consumed in two ways. One is work done by the system on the surroundings, and second is change of internal energy. When I use the word internal energy, it is a combination of both molecular potential energy and molecular kinetic energy. Molecular potential energy is a function of volume, and molecular kinetic energy is a function of temperature. This also I have taught you in the previous classes. After learning those things, we have done a lot of numericals where we used first law of thermodynamics. I think last two sessions where I'm meeting you, we are focusing more on numerical solving only from first law of thermodynamics. And then we learned about processes, various processes, isothermal, adiabatic, isochoric, isobaric, and each process, how is the first law of thermodynamics applied and how to find the work done. So all these things we have seen till now in these classes. Again, if somebody has not yet seen the videos properly, taken the notes properly, then definitely you are going to struggle in these chapters. Believe me, this whole part starts from thermal properties of matter till KTG are once again easy chapters for those who are understanding it. Otherwise, you will leave this chapter, not only now, forever. Even if you go for NEET and JEE in future, I have seen children, I mean, they are leaving these topics, thermal properties of matter, thermodynamics, all these things are leaving. KTG and all, they're leaving and going, thinking it is too complex. But KTG is a scoring chapter. If a question comes, you can easily attempt it. One question may only come in JEE, and in NEET, certainly one question will come. In JEE, one question may come. In NEET, certainly one question will come. And if you are missing the question from KTG, then again, shame on you, because very simple chapter, very simple chapter. Nothing much is there in this chapter. So again, I'm saying it is a continuation of the previous chapters. So I'll try to keep it simple, but you can understand it very clearly only if you have if you have attended the last classes. Otherwise, there will be some struggle. Let me check how much I'm able to clear that struggle. Okay. So this chapter, if I say, basically what we are going to learn in this chapter in KTG, we are going to learn only few things. And the first topic, the main topic, which we'll start with, finding the pressure exerted by the gas on a cylinder, container. Pressure exerted by gas on walls of containers. So we will derive and get the formula of how much is the pressure exerted. Up to now, pressure for you is force upon area, used in solids mainly. Pressure is also equal to rho gh, used in liquids mainly. And gas, neither we will use rho gh nor we will use force by area. We are going to use a new formula which is actually a result of F by A only. Even if pressure is equal to rho gh has been derived by using force by area only, if you remember. Pressure is equal to force by area. From there only we have found force as mg and area we found in terms of density, and then we converted and wrote pressure is equal to mgh, that is rho gh. So same way here we will also derive a formula, and a new formula will come which will help you to find how much is the pressure exerted by the gas on the walls of a container. Then in this chapter we will learn about what is kinetic interpretation of temperature. Again, an important topic for the competitive examination. Kinetic interpretation of temperature. It means we'll come to know that how temperature can impart energy on a particular gas. Obviously, it is true that if you put temperature, gas will become more fast, it will become more fast, it will have more energy, but how much energy? Is energy same for all kinds of gases? No. It totally depends upon the gas type, whether it is a monatomic gas, diatomic gas, triatomic gas, linear, triatomic, non-linear, polyatomic. Those things we will learn today. That how to interpret the kinetic energy of a gas due to its temperature. It is a formula that relates that. Learn about that formula. This comes also in, I think, 12th standard, where suddenly we use E is equal to 3 by 2 kT. Somewhere we have used this, if I am right. That is the formula. E is equal to 3 by 2 kT. You remember this? 12 people who are sitting here, they may know. Boltzmann constant is Kb. This formula we have used in 12th also, somewhere. It comes from 11th. And this formula, if you find the result, it will become 1 by 3 rho into Vrms square. Vrms square. This is the formula. This is the formula for pressure you will be getting after you solve the whole, derivation will do. And then in this chapter, we are going to learn about degree of freedom. Interesting topic, easy topic, simple topic, if you understand well properly. Degree of freedom of each gas. If it is a monatomic gas, what is the degree of freedom? Diatomic gas, triatomic linear, triatomic nonlinear, polyatomic. How to find the degree of freedom of any gas? We'll do that. After knowing what is the degree of freedom, we will apply degree of freedom and find the partitions of energy. That is called as law of equipartition of energy. Law of equipartition of energy, where you will learn how humble is our nature. It never does any discrimination, and how the nature supplies equal opportunity for all the degree of freedoms. I'll teach you, then you'll understand what I'm trying to say now. So this theorem will say that each degree of freedom will have a certain amount of energy. So based upon degree of freedom, different gases have different amount of energy. All the gases have not same energy. They have different energy purely based upon what is their degree of freedom. We will learn that today. Then we will learn about specific heat of gases. Specific heat of gas, where we are going to learn about gamma. Cp by Cv is there, right? So we'll find the ratio, we'll find Cp, we'll find Cv, and then we'll find gamma, which is the ratio of Cp by Cv. If you remember, gamma is Cp by Cv. Remember this? We have learned in the previous chapter itself. Gamma is equal to Cp by Cv. Cp is specific heat of gas at a constant pressure, and Cv is specific heat of gas at a constant volume, temperature volume. Cp is always more than Cv, reason also I told you, and Cp minus Cv is equal to R. R is called as gas constant, 8.31, isn't it? That we have learned, and we will apply those things and find the specific heat of gas. And again, each gas has different specific heat, each gas has different gamma values. So what is the gamma of diatomic, triatomic, linear, triatomic, nonlinear, monatomic? We will find that also. And final topic of this chapter is mean free path, where we will learn that if suppose there is a container having, or let me assume that gas is moving in this room. So obviously when I'm speaking to you, I'm vibrating from my mouth, and there is energy is traveling from me to you through waves. And then The particles in the room, the gas particles, do you think they are at rest? No, they're in constant motion. We're not feeling it, but obviously they're in constant motion. And there are millions of gas molecules inside. They are moving here and there. And since there are millions of gas molecules, there is a chance of collision, isn't it? So how much is the length or distance it travels without colliding with the next particle is called as mean free path. Mean, why? Because we will find the mean of all the distances. Each particle will not go and hit the other particle in the same time. One thing may take 1 microsecond, one thing may 2 microsecond, one thing may take 3 microsecond. So average of all these free paths, single free paths, is called as mean free path. Today we will try to find the value of mean free path also. This is the whole chapter. So I have done 6 parts, right? 6 topics are there. So if you know the 6 topics, done. I have even told the basic gist to you about what you're going to learn in this chapter. Fine. So we'll go one by one and we'll learn all these things. That is pressure, how much a gas exerts a pressure on the container of any material, how much pressure it exerts. We'll find what is the kinetic interpretation of temperature, degree of freedom of different gases. We'll apply degree of freedom and find what is law of equipartition of energy. Then we will go to specific heat of gas, and finally we'll talk about the mean free path. I hope you're clear in what is the aim of today's class, what you're going to learn, right? Shall we proceed further? Okay. So without wasting further time, those who are there in online, I hope you are listening to me clearly. If there is any problem, you can ask me. We are entering the subject. So first, I hope you're understanding. I said this to you, that gas molecules are not like solid molecules, not even like liquid molecules. Liquid molecules are also very far from each other. They're free to move, but not as free as gas. So gas molecules are like this, random motion. So it is always said that you can define the volume of solid, you can define the volume of liquids, but can you define volume of gas? You cannot define itself, because gas will occupy the volume where you are keeping it. If you are keeping the gas in a bigger volume, it will occupy a bigger volume. How much volume of gas is there? What is the size of the room? Now if I ask you how much volume of gas is there in this room, what will be your answer? What is the room size? You will find its volume. That is gas is there. That is your answer, isn't it? Or can you say this much gram? You cannot say. Reason is this is actually called as virtual volume of the gas, because real volume, if you take, it will be very less, very less. Suppose if I am having a container like this, the same thing that I have drawn here. Let me draw 3-dimensional like this, right? So if suppose in this container I keep 8 molecules of gas, any gas, I am keeping only 8 molecules. Theoretically, practically not possible. If I am keeping 8 molecules, they will go and surround like this, maybe like this. So what is the volume of these gases? The whole volume of the cylinder, not cylinder, cube. If I take all these molecules separately and arrange them like this, 1, 2, 3, 4, 5, 6, and find its volume, you cannot say the number, but whatever value you find, that volume will be way lesser than the original volume of the container, right? So this is what I'm trying to say, that the real volume of gas in this picture itself, you can see how much ever molecules are there. I mean, we can count maybe some 15-20 molecules are there, and all these 15-20 molecules volume, if you add up, that will be much lesser than the volume of this cuboid, in this case rectangle here. Volume you cannot find of it, but if you take it as a cuboid and find its volume, it will be very lesser than the real volume of the gas molecule. I hope you're understanding what I'm trying to tell you. So that's what the gases are. That's how they behave. Then, as I said to you, that the size of the gas molecule compared to the distance between them is very small. So if I take small d as distance of the diameter of the gas molecule, and capital D as the distance between the gas molecule, the distance between the gas molecule is once again much bigger than the distance, that is the diameter of each gas molecule. So yes, here, see, this chapter name is Kinetic Theory of Gas, isn't it? So whatever theory we are going to learn in this chapter, there will be some assumptions for that theory. So the first assumption that we will do, even for deriving the pressure, is going to be this, that whatever collisions are happening between the molecules or between the molecule and the wall is assumed to be perfectly elastic. Now, perfectly elastic collision, you should remember from work energy and power, where there is no loss of kinetic energy. Why momentum? Kinetic energy. Kinetic energy is conserved in elastic collision. That is kinetic energy before collision, kinetic energy or velocity also we can say. What is the velocity? If I'm throwing at 5 meter per second, if it rebounds at 5 meter per second, it is elastic collision. Practically not possible, but theoretically anything is possible, right? So we'll assume that, and also the time spent during the collision is negligibly small, very small. These assumptions we are going to make for a particular gas molecule. Here, if you see the diagram, whatever velocity it takes, the same velocity it will come back. That is the assumption we are going to make in this derivation. In this chapter, all derivations, we are going to assume that the gas molecule, when it hits the wall of the container, then it undergoes elastic collision. Since it is elastic collision, the velocity is going to remain same after the collision also. So obviously it obeys Newton's laws of motion. We'll assume it to be obeying Newton's laws of motion. So here I have given you two formula. This formula is not required for school exam at all, but I have included later only for you people. Are you aware about this? The velocity of this is called as most probable velocity. It is not there in school syllabus itself. This velocity is called as most probable velocity of gas molecule, and this is called as mean velocity of gas. In the syllabus, what we have is only RMS velocity of gas, which you're come fast. Sit here. So in syllabus, we have only RMS velocity that you will derive now, RMS velocity. But you should also know VMP. VMP is most probable velocity of gas, which is equal to root over 2 RT by M. M is the molecular mass. M is the molecular mass, and R is gas constant, T is the absolute temperature. And this formula, mean velocity or average velocity also we say this. This is root 8 RT by pi M. Now, those who are preparing for competitive examination, they can write this. If your aim is only school exam, need not to worry about this, because it is not required for school exams. It is not there in syllabus. But those AR actually they have taken for argon, where I took from somewhere and pasted here. This is not to be considered. It is just molecular mass. Okay. So the formula is root over 2 RT by M, where R is gas constant, T is the temperature, absolute temperature, and M is the molecular mass of the gas. Right, Sai Akhilesh?
Yes, sir.
And mean velocity or average velocity is root over 8 RT by pi into M. So we will compare today the molecular mass. What? You are different, man. You are different. You are different means the state board is different from all the boards, including ICSE and yeah. Anshul.
We won't take delta T here, like I won't be.
What? Come again?
Like delta T, why are we not using change in temperature?
Temperature is not there here. Only we are taking absolute temperature. This is going to give you at a particular temperature what is the velocity. That's what it is going to give you. If I am going to give 40 degrees Celsius, what is the velocity of the gas? Most probable velocity of the gas. This formula will give you. This formula is not for finding the change in velocity because of temperature. This formula is giving you velocity at a particular temperature. Are you getting, Anshul?
Yes, sir.
Yes. So I'm going to the next slide, and one question was there. Now you can find the answer very easily if you know the value of R and T. But I'm not going to solve this question now. Leave it, because it's just formula-based question. Put the value of R, T. R is given. R is known to 8.31. T is given to you. Put in the formula, get the answer. Nothing else is there in this. So when you have put in the formula, you will get the VMP. That's from here only I pasted it. So argon was written there. So argon gas. And same way, if you are going to find the average speed, then it is going to come. So they are different. So mean velocity of argon gas is around 397, that is 400 meter per second. But mean most probable velocity of argon gas is around 352. If I am going to find RMS velocity of argon gas, that will be again third value. Okay. So this is most probable velocity and mean velocity. Let us enter into our today's topic. That is pressure calculation and kinetic interpretation of temperature. So as I said we are going to learn about the pressure calculations. So before going into the main topic, you must know what is the meaning of RMS speed. So you can write it down, all of you, those who are sitting here and sitting in the online, take the definition. As the name says, root mean square. So RMS value of a set of values is the root square root of the arithmetic mean of the squares of the values. They have defined what is the meaning of RMS. So in the case of velocity, if you take the root of square mean, that is v1 square plus v2 square plus v3 square plus vn square by n, you are going to get the RMS velocity of the gas. Remember this. It means that if you have gas molecules moving with velocity v1 here, with velocity v2, other molecule is moving with velocity v3, and if you want to find the RMS velocity, root means square velocity, then that is going to be the square of mean of velocities of individual molecules. So v1 square plus v2 square plus c3 square plus vn square by n root over is going to give you RMS velocity of gases. Also the kinetic energy of the gas, obviously half mv square. So that is also the total kinetic energy of all the molecules. They have talked about the total kinetic energy, not the average. Number of which one? Where is n here, man? N is total number of molecules, not moles. Number of molecules are different from number of moles. Yes, obviously mean is there. No? What is the meaning of mean? Shall I proceed further? Make it fast, man. I want to finish a lot of topics. Shall I proceed further, Varshika? Make it fast, I will wait for a minute. Done. Can I? Okay. So next we are going to derive the pressure of an ideal gas. For that, what we have done, we have taken a particular container of length L or any length A, D, B, C, anything you can take, and we are going to consider a single molecule. Okay, and then we can multiply with n molecules to get a total pressure exerted. But now what I'm going to do, you may ask me one thing, sir, whether this molecule will go towards x direction, y direction, z direction, or any random direction. How do you define that? We cannot define that. It can go in any direction. So usually, if you take the velocity will have three components. Those three components would be Vx, Vy, Vz. Or you can write Vx I cap plus Vj y cap, z cap, k cap also. So it has three components. It can go anywhere. So what I will do, I will first try to find that if this particle, this gas particle, would have gone in x direction and hit this plane, this can be called as yz plane. If this is x direction, this is a yz plane, these two planes are yz planes. So I'll try to find what is the pressure exerted on the yz plane. Same way, when the gas molecule would have come in z direction, then what is the pressure exerted on xy plane? That we will find. And then what is the pressure exerted if the gas would have moved in y direction, and what is the pressure exertion on xz plane? We'll find all these three pressures and find the mean of it, and we'll say this is the pressure exerted by the molecule on the walls of a container. Are you getting what I'm trying to do? What I'm going to derive now, is it clear to you? What I'm going to do, I'm going to find pressure exerted by this gas molecule in x direction. If the gas molecule moves in x direction, So pressure exerted on this wall. Which wall? Wall in YZ plane. Same way, if the gas molecule would have moved in Z direction, then what is the pressure it exerts on XY plane? And if the gas molecule would have gone in Y direction, then what is the pressure exerted on XZ plane? Don't worry, we'll do one and we'll do write similarly and it will be easy. Okay, so we'll take one X direction we'll take and we'll try to find. So first what I am assuming the molecule, gas molecule to move in X direction. So for gas molecule to move in X direction with velocity, how much? Vx, right? Pay attention, I'll give time for writing. First to learn how I'm doing, I'll stop in between and I'll give time for writing. Understand this basic derivations and it helps you. So what will be the, see, I'll tell the derivation itself to you, the logic, then you can do very simply. What I'm going to do, I'm going to find pressure, and you know pressure is equal to force upon area. So area we know, if I'm taking this as L, this area of the side will be L square, right? Any side will have L square area. So area is known to us. Force we want to find. And what is force formula? Force formula is rate of change of momentum. That is change in momentum by time. Yeah, rate of change of momentum, I am writing change in momentum by time. So what I'll do, I will find if this gas molecule starts from origin, sorry, goes and hits the wall, comes back, what is the change in momentum I will find? Initial momentum will be how much? Something. What is the value of it? mv. So m into vx. What will be the final momentum? Very good. Minus mvx. Why minus mvx? Direction is changing. What will be change in momentum? How zero, man? Change in momentum? 2 mvx. So we are going to get change in momentum as 2 mvx. Now itself I've told you. Time I can find. This length is L. So how much time it takes to go and come? So distance will be L plus L2L and velocity is Vx. Velocity is given by time. Time will become equal to 2L by Vx. You got it? Put here, get the answer. I said you the whole derivation itself. I'll do it one step by step. So first I'm going to find change in momentum. For finding change in momentum, don't you think it will become equal to mvx minus of minus mvx? I hope all of you are understanding this. Initial momentum, mvx in this direction. After it hits and comes back, velocity will become minus mvx. So momentum will become minus of mvx. Subtract both, you will get mvx minus of minus mvx. It will become equal to 2 mvx. Or initial momentum minus, both you can take. One negative will come if you want, if you say like that. We'll take its magnitude only anyhow. So it's going to be 2 mvx only, the magnitude. And time. Time will become equal to L will become 2L, and velocity will become Vx. Do you agree? So we found change in momentum, we found time. What will be the force exerted on YZ plane? That will become equal to change in momentum by area. That will become equal to 2 mvx by 2L. Above what will go? Vx will go, right? 2 gets cancelled. It will become mvx square by L. Do you agree? This is the force exerted on the YZ plane by one molecule of gas. Yes, for n molecules, what will happen? Into n you will get F on YZ will become equal to n into m into Vx square. Why Vy you went by L, right? Only YZ only I'm doing now. Then if you want to find the value of pressure, force by area, so what will be the pressure on the YZ plane? Divided by L square. It will become n into m into Vx square divided by L cube. Anybody has any doubt in this what I have done? Very simple. Pressure is force by area. Force is change in momentum by time. Change in momentum is initial momentum minus final momentum. We found initial momentum, we found final momentum, subtracted both, we got change in momentum. Then we found time taken for this, which we got it as 2L by Vx, divided both, got the force. For n molecules, got the force. For n molecules, got the pressure. So now I have got what is the pressure exerted on YZ plane by n molecules, that is equal to nm Vx square by L cube. I hope you agree with this. Any problem? No? Take 2 minutes of time and copy. Those who are writing for the first time, take 2 minutes, not more than that, and copy fast. Then I go to the next page.
Sir, n we will not take n by 2.
Why n by 2, man?
Sir, in our book, half of the molecules will move
That
right
is,
hand side and half of the molecules will move in left hand side. They taken, sir.
they would have taken that. Now let me complete the derivation, then we will talk about that.
Okay, sir.
Okay. So in your book, what is the final answer they have come with? Sayakilesh.
Don't know, sir.
Oh, book is there in front nearby, you know. Take the book and see what is the final pressure they have got. Unmute yourself.
Sir, I will take and come the book, sir.
Yeah, take and come the book, no problem. Yes.
1 by 3 nm v square v rms square, sir.
1 by 3.
nm v rms square, sir.
Okay. You just see whether the same answer is coming or not. Okay.
Okay, sir.
Written. Fast, please.
This lesson important, sir.
No, man, don't study. You can drop off. Why, Bas Sugindran?
No, sir. In school, they didn't teach this lesson till now.
You are learning now, right? That's why you are coming here, no?
Sir.
Then whatever I am teaching is important. Why you are asking this question itself? If you, and that too, you, I think you had an aim of writing JEE after 1 year, right?
Yes, sir. Yes, sir.
Still have that aim or left that aim itself?
Having, sir.
Then definitely it is very important, man. If you are not going to do anything, 12th marks, then not important. But if you are going to appear for any competitive examination, every chapter is important.
Okay, sir.
Yes. Shall I proceed further? Okay. Yeah. Fast, Kirti. I am waiting. Yes. Everybody here also? Okay. So, I'll erase the whole board. I cannot bring it back, okay? No undo here. Let's remember the form nm Vx square by L cube. So, we have got P. Yes, we have got P YZ, isn't it? YZ as n m Vx square by L cube. This is only for the YZ direction. Same way, you tell me what will be Pxz. Don't you think it will be n m Vy square by L cube? And same derivation, Pyz will become equal to sorry, Pyx xy n m Vz square by L cube. I hope you are agreeing with me. Now, if I find the mean of all these things, P, that will become equal to Pyz plus Pxz plus Pxy divided by 3. So, how much I am going to get? Check. We are going to get 1 by 3 times, take nm common, n into m common. So, what will remain here? Vx square plus Vy square plus Vz square. This is only called as VRMS. So 1 by 3 n m L cube also is there. Yes, yes, sorry. Yeah, divided by L cube also is there. L cube into N M into V RMS square. This is the formula of pressure exerted by any any ideal gas on the walls of the container. One more thing. Here if you see N into M. M is what? Mass of, what was M here? Mass of one molecule of gas. No, M is molecular mass. That's mass of one molecule of gas. And if you multiply with N, how much you will get? Total mass, isn't it? N molecules are there. So I am assuming same gas. I am not assuming a mixture of gas. Remember that. So P will become equal to 1 by 3 times N into M will become, I am writing capital M. Capital M by L cube. What is L cube? Volume. So what is the mass by volume? Obviously density, right? Pressure you are saying. So pressure will become equal to 1 by 3 rho V RMS square. This is called as the pressure exerted by any gas on the containers because of its motion. How much will be that? 1 by 3 rho V RMS square. From here only we will find V RMS itself. I'll do it upcoming pages. But is it clear to you? I hope it is. Complete the derivation fast. Akhilesh, we came to the same conclusion.
Yes, sir.
There can be different ways of solving, but the end result will remain the same. If we take out the
N is the number of molecules.
yeah,
So if you take out N, that's only for one molecule. The one you will
obviously. Let me know if you are done. The end result is important. 1 by 3 rho V RMS square pressure. It will be used in some questions. Shall I proceed further? Not much is there on this board. Varshika here? I can? Avinash, shall I? I can erase the board, no? No undo here. Okay. These things we did. Okay. Now, let us talk about the kinetic interpretation of temperature. So, give the heading as kinetic interpretation of temperature. I said you here you're going to find for what temperature, how much energy a gas acquires. That is what we're going to learn in this. So, the heading is kinetic interpretation of temperature. So, just now we have derived this. That is pressure exerted by the gas is 1 by 3 times rho into V RMS square. And also we know that density is equal to mass by volume. Just now we did. Okay. So, if you see, I can write from here, I can write density is equal to mass by volume, and volume I will send that side. I will write PV is equal to 1 by 3 m into R V RMS square. Can I write like this? This step is clear to everybody what I have done. Instead of density, I am writing mass by volume, and volume I am sending this side. So P into V will become equal to 1 by 3 m V RMS square. I hope you are understanding what I am going to do now. PV is equal to nRT I am going to use. That's what I am going to do. No doubt in that. So we know that PV is equal to nRT, where n is the number of moles. For 1 mole, PV is equal to RT. So I will replace PV with RT now, and I will write RT is equal to 1 by 3 m V RMS square. I hope you understand what I am doing. And then from here, I can write that temperature is equal to 1 by 3 m R I will bring down V RMS square. This relation is again very, very important for the competitive examination also, where remember that temperature is proportional to V RMS square, because see, m of the gas is constant, R is a gas constant, 1 by 3 is a constant, so T is proportional to V RMS square. So if temperature is changed double, 4 times, like that questions will come. So remember that the relationship between temperature and V RMS is proportional to V RMS square. Coming back. So yes, same thing that I wrote, they wrote now. Temperature of gas is due to its motion Vrms and vibrations only. So as Vrms will increase, temperature will also increase, or both vice versa. Yeah, vice versa. If temperature is increasing, RMS velocity is increasing, or if RMS velocity is increasing, temperature will also increase. So if you have an object, suppose the molecules by any means starts moving more faster, it will become hot. Or if I supply heat to it, the molecules will become more faster. Vice versa. They are both are applicable. By any means you can make it fast. Sometimes without even giving heat to it, by using some magnetic forces and all, you can make it fast. In that case, you will feel I am giving magnetic force, but it is becoming hot. Why it is becoming hot? Vrms is increasing, so temperature will increase. That's what we do know in the case of magnetic induction. We are using magnetic field to increase the temperature. Yes, so can I proceed further? Copy fast. Don't take much time. In this page, that is very important. Vrms square is proportional to T. And from here you see, those who want to see, Vrms can also be written as root over 3 RT by M, isn't it? That is the formula of Vrms. We will convert into this also now, Kb also, Boltzmann constant. Let me know if you are done. Those who are writing for the first time, finished writing. Please make it fast if you have not done. Can I proceed further? Kirti, done?
Yes, sir.
Anbarsi, still writing or done?
Done, sir.
Okay, I'll proceed to the next page then. Right. So now comes a very important part. Again, competitive people, this part is important for you. So we have the kinetic energy of the gas as half mv square, isn't it? In this half, I am multiplying and dividing by 3. What I am doing, try to understand. Kinetic energy is half mv square. In this half, I am multiplying by 3 and dividing by 3. What I am doing, understanding? Why? Let us see. So before this page, we got a point where we wrote P is equal to 1 by 3 m by v into Vrms square, right? PV is equal to 1 by 3 m, same thing. So then, instead of writing same thing they are writing, next step will come. Yes. So now what did you see? Kinetic energy, instead of writing 1 by 3 m Vrms square, they are writing PV. So can I say that kinetic energy becomes equal to 3 by 2 PV? What has happened? I hope you are understanding. Just the changing of terms from here to there. I want to now draw a relationship between kinetic energy and Vrms. Okay. So kinetic energy is equal to 3 by 2 PV. Next, for ideal gas, PV is equal to nRT. For 1 mole, PV is equal to RT. And 1 molecule, PV is equal to R by N into T. This you know or not? Don't know this relation between moles and Avogadro number, you don't know. Chemistry, what? Anything you should know. So for 1 mole, PV is equal to RT. For 1 molecule, PV will be equal to RT divided by Na, Avogadro number. If you don't know this relation, you should know. Yeah, 6.02 to 10 power 23, if I'm right. 23 or 22? 24. 23 only, if I'm right. Yes. Okay, whatever. So, yes. 1 second. So, N is the Avogadro number. And this R by Na is a constant. It is called as Boltzmann constant Kb. Remember these things. What is Kb? Kb is R by Na. R is gas constant, N is the Avogadro number. When you divide gas constant by Avogadro number, you get a new constant called as Boltzmann constant. Please remember this. So now, if I replace by Kb, then Pv will become equal to Kbt. If Pv became equal to Kbt, from these two equations, Pv and there we have kinetic energy, we can write instead of Pv, Kbt. So kinetic energy will become 3 by 2 kT. I wrote on the first page itself. Kinetic energy is equal to 3 by 2 kT. This is we are using in 12th also. Which chapter we are using this, but I am not able to remember now. No. Question will even theory itself we are deriving by this. Some chapter we have used this if I am right. Electric field and charge. No. Somewhere in magnetism we have used. Okay, I don't remember now. But somewhere we have used if I am very right. It is there in 12th also. Okay, whatever. Kinetic energy is 3 by 2 kT. Please remember this. How it has come, I have derived it and shown you here. So kinetic energy is 3 by 2 kT. I can write some more things which is not written here. So instead of writing kinetic energy, if I replace with half mv square, so it will become half mv square, obviously V RMS square, is equal to 3 by 2 kT, right? 2 gets cancelled. We can write the VRMS formula from here. VRMS will become equal to 3 kT by m root over. They'll use in some questions. VRMS is equal to 3 kT by m. Now Boltzmann constant is known to you. Temperature is what you are giving, and m is the mass, molecular mass, obviously. So by this we can find the mass of that we solved. No, that first question, argon gas. So for that temperature we can find the velocity. We will get the VRMS. If you remember the first page, which I told not much important, where we found the most probable velocity and the average velocity, the two different formula. Third formula is this, root 3 kT by m. So there are three kinds of velocities that can come in kTg. One is most probable velocity, one is mean velocity or average velocity, and third is RMS velocity. RMS velocity v1 square plus v2 square plus v3 square by n root over. That will not be used in any question, only theoretical importance. Sorry. In exam, what will be asked is this only, 3 by 2 kT. Clear? Have you copied this? Make it fast, please.
Boltzmann's constant, right?
Yes, Boltzmann constant.
So if we know the temperature, you can find the kinetic energy.
Obviously. You can find the velocity also.
Yeah, we know kinetic energy.
Velocity also. Both. That's what it, huh?
Further, we need to know the mass, right?
Obviously, which gas you're talking, that will tell the mass, no? Oxygen will have a different kinetic energy, argon will have a different, and nitrogen will have a different. Different gas will have different energy and different velocities also. Like for example, if you put T as 300 and put Boltzmann constant value here, and you find for velocity for nitrogen gas, it will come 516 meter per second. I remember somewhere I have read this. 516 meter per second is the velocity of nitrogen gas at 300 Kelvin temperature, room temperature, 27 degrees Celsius. Like that you can find for any gas if you know its molecular mass.
We know the gas.
Obviously, if you know the gas, you know its m. If you know its m for the temperature, what is its velocity, you can say. Clear? Any doubt on this? Very basic things we are learning. Again, this this page looks like too much formula, but it's not some complicated thing. Just rearranging of terms is happening, nothing else. Can I proceed further? Shall I? Sure. Okay, thank you. Yes. So, yes, the same thing that we wrote there, I have written here. That is, I wrote there, they have written here. VRMS is equal to 3 kT by m. And this, if they want to divide by Avogadro number, then why they are doing this? Actually, they want to write in terms of R. The same thing they will do now. See, they will write in terms of R. So 3 RT by m not also can be written. Instead of writing 3 kT by, see there they have written no 3 kT by m. If you want to write in terms of R, then it will become equal to root over 3 RT by m. Is it clear? You can write just this formula you can write if you want to write also for one mole of gas. They would have taken for 1 mole of gas only. And finally, we have the relationship, all three formula. Which is the maximum? Least is most probable velocity. So if I write the formula, these are the formulas we have learned. See. So root 3 RT by m, root 8 RT by pi m naught, and root 2 RT by m naught. This again is important only for competitive examination. There is no mention of this in the school. NCERT book is not, no mention is there. So those who are preparing for any exam, they can write this. Question can come directly from here also, if your luck is good. So the maximum value is RMS velocity and the minimum value is most probable velocity. And the formula also I once again mentioned here, 2 RT by m, 8 RT by pi m, 3 RT by m. Okay. Can I proceed little further? I hope you have written the three formula. You already wrote just the order, maximum and minimum. Okay, I hope you have written. Now take this question, very basic question, but solve it. One question. Nitrogen, I told the answer also now. Anyhow, solve it. Everything is mentioned there. STP means standard temperature and pressure. 10 to the power 5 Pascal will be the pressure. Tell me the answer. RMS speed of nitrogen at STP. But they have taken temperature as 0 degrees Celsius. Then also you see. Why density is given? Think.
ATM. So 10 to the power 5.
Yes, ATM means atmospheric pressure 10 to the power 5 Pascals. Any answer?
Nearly.
I hope you are using this formula. 3 RT by m, RT will become PV. Right?
Yeah, that comes down.
Because PV is equal to RT. So,
instead of m by v, we are using density.
yes. So m by v will become density.
1 to 1.25.
Over.
Yeah, I'm there.
Now just solving approximately. You solve 490 meter per second. So see, I nowhere told this formula itself to you, 3 PV by m. But question came from 3 PV by m. Because it is expected for you to remember that PV is equal to RT. You cannot say, I do not taught this formula itself. I taught 3 RT by m, right? If you're not able to write instead of RT PV, then something is very lacking. Are you getting my point? How the answer has come? Instead of RT, they have used PV and the same answer has come. Same answer means P is known to you, V and M can become density and density is known to you. Density, if I put 1.25, you'll get the answer. Okay? Is it clear? People sitting here? Sure? Very basic thing, nothing big I'm doing. Who are in online, I hope you're understanding what we're learning. Any problem in this? Can I proceed further? Do you permit me? Shall I go further?
Yes, sir.
Thank you. So, oh, one more question is there. Which of the following parameters is same for the molecules of all gases at given temperature?
Sir, kinetic energy, sir.
Kinetic energy, then speed also, right?
What? Kinetic energy?
Speed and kinetic energy.
Which of the following? Which of the following?
Which of the following?
As a more than you're saying.
Yeah, both. With kinetic energy, then it should be speed also, right?
Sir, only kinetic energy, sir.
Why?
Actually, speed also, velocity should be there actually. Because kinetic energy is a factor, then velocity also should be a factor, isn't it? Because kinetic energy is half mv square. Yes.
Different gases means mass increase, sir, but velocity will decrease, no, sir.
Different masses, different gases.
Sir, kinetic energy constant, sir. For different masses, mass will be different, sir. So surely velocity also must be different, no, sir.
Point, no? If mass is going to be different for different gases, velocity is also going to be. Yes, so what is going to be constant? Kinetic energy is going to be constant. Yes. Next question, fast, 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 fast. Next question. RMS velocity of oxygen is given as 500 meter per second. Don't know anything about oxygen.
No, like mass and all.
Oxygen mass you don't know.
No, I don't remember that.
Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. 8 is the mass, atomic number. What is the mass number then? Very difficult one.
16 AM.
Sir, 2000 M/s, sir.
2000 meter per second you are saying.
Yes, sir.
Hmm? Anybody else who has any answer?
What did you say?
2000 meter per second.
I have got the same.
Oh, agreeing with that, Pratap?
Yes, sir.
Okay. Anybody else sitting here? That follow-based question. 2000 meter per second. Obviously, you should certainly remember, and oxygen gas will not will be like O alone. It is O2, so it will be 32, isn't it? Same way hydrogen gas, it will be H2, it will be 2. So when you put in the formula and get, you will get the answer as 2000 meter per second. Anyways,
Because they are two.
in this case, it worked for you. I know they would have also not taken this 2 and 32, but concept cannot be changed, no man. Yeah, if it is diatomic, triatomic, it will be something else. So you should be very careful about the gas is diatomic gas, monatomic gas, or another thing. Hydrogen and oxygen both are diatomic. So we are taking 2 oxygen and 2 hydrogen. Did you use this Akhilesh?
No, sir. I thought, but I put a root of 1/16 only, sir.
What about you, Pratap? Did you use this?
I used 32.
Good then. If you use, then it is good. Because oxygen will not be having only nascent oxygen, only 16. It will be 32. Fine. Shall I proceed further? Yes. So now comes the next part of this chapter, which is degree of freedom. Interesting topic, simple topic also. So you must understand that gases exist in different forms. We have monatomic gas where there is only one atom of a gas. We have diatomic gas where there are 2 atoms of a gas. We have triatomic gas where we have 3 atoms. When it becomes 3 atoms, then we have options. Those 3 atoms can be in linear shape, or those 3 atoms can be in non-linear shape. This is called as linear triatomic, isn't it? It can also be like this. What is this? Non-linear triatomic. Okay. So what is the meaning of degree of freedom? First understand that. Degree of freedom means in how much degrees or in how much directions your particular object is allowed to freely move. That is called as degree of freedom, as the name is saying, degree of freedom. In how many degrees it is allowed to move. For example, if you take this door can open in how many directions? 90 degree it can move. Only one direction it can move. Yeah, 90 to the application of force you are saying. So it has only 1 degree of freedom, isn't it? Can it move like this, up or down? Obviously.
But 2 dimension it can move, right?
2 dimension is you are telling it can move in a plane. In a plane. But it can it move in directions? Like for example, can it move in this direction, up, down? Can it move right, left? They cannot see, I understand, man. You're worried about them. I'm worrying about you. Okay. See, one boy sitting here, one sympathetic, he's saying, sir, what you are showing, they are not able to see. Give some other example. Okay. So I will give this example. You are able to see this now, guys, who are in online? this remote. If I hold the remote like this one side, not fixing it, hinging it means allowing it to move. Okay. Now, if this remote can move in this direction, that is the only degree of freedom it has. It cannot neither move up or down, neither it can move front or back. It has to be like this only. So its degree of freedom will be 1. Or if I would have allowed it to rotate, that also is a degree of freedom only. So degree of freedom means in how many directions or in how many ways a particular gas molecule can show its motion. That's why it's called as degree of freedom. Okay. So, I mean, if you see the technical definition, it is defined as the total number of independent variables required to describe the position and configuration of a system. Technically, if you want to write definition of degree of freedom, it is the total number of independent variables required to describe the position and configuration of a system. Please make a note of it. The definition of degree of freedom, those who are writing for the first time for school syllabus. One more example. Simple pendulum. How many degree of freedom? 1. Again, it is moving in a plane only, as you are thinking. But its degree of freedom is only 1. Because it is not allowed to move like this.
What if it's like this?
If it is allowed to move, it will have 1 more degree of freedom. But here they are saying
Simple pendulum, so it moves
only 1 direction. So it has only 1 degree of freedom. Degree of freedom is how much ways it is allowed to move. Are you getting? Another example take. See what is happening. Ant is coming out, right? Ant only, no man.
Yeah, it is hand.
It's some kind of traumatic photo. GIF. Okay. So how many degree of freedom the ant is having? They are saying 2 degree of freedom ant is having. It cannot fly above, right?
1, sir.
1. How 1 you are saying?
That's 2.
Actually, it can move in XY plane. It can move, isn't it? Anywhere it can go. Not like this. See, this pendulum cannot go in anywhere. It can go only in one way. It can go in this plane in a multiple number of ways, but it cannot jump and go above until it has wings and it can fly.
Sir,
Yeah, but I'm not
3 degree
sure.
of freedom, sir.
What, man?
3 degree of freedom, sir.
For ant, you are saying?
Yes, sir. Coming out of hole, sir. Saving you, sir.
Yeah. Okay. If you imagine this hole is deep inside, then yes, 3 degree of freedom.
Yeah.
It's yeah, in that way you say. If you take only this 2-dimensional board, and again 2 degree of freedom only. Okay, another example is there. This is about this bird. Bird is 3 dimensional. Like I said, wing with that same ant. If it gets wing, it is 3 degree of freedom only, isn't it? Because it can go above. So very basic understanding of degree of freedom. We'll apply this logic to gases. So what we're going to do? Oh, directly this is came.
That's not.
No, I'll do it. Yes. Monatomic molecule. So see this gas molecule. Single atom is there. How it is moving? One direction. It can move in Y also. It can move in Z also. But only one direction it can move. That is its degree of freedom. So can I say it is a degree of freedom is only 1? It can move in X.
No, sir.
It can move in Y. It can move in Z. Isn't it? It can move like this also, no man? Or it can move like this also. So how many ways this gas molecule can move? 3 ways. So what will be its degree of freedom? 3. That is understanding by diagram. But always you cannot have this kind of, now we have this board, so I'm showing you.
I have a doubt, sir.
Please.
Anywhere in the plane, sir.
Can it move?
Anywhere in the
It can move. It can move in XZ plane, YZ plane, XY, like how ants are moving, no? It can move. But it can move in all 3-dimensional plane. Isn't it? Gas molecule, it's not restricted to only surface. Like how Nilesh told, that is actually sarcasm kind of thing, which is whole. But if it is a plane, if I am leaving an ant on this surface, you may say, sir, it will go climb at the wall. But when it is climbing the wall, that only it can climb that wall, no? It cannot have a degree of freedom by jumping, flying like that.
What about the chair? It's part of the movement.
Climb the chair.
Climb from chair.
Then again, degree of freedom will change in that direction alone, it will be there. Are you getting my point? If the ant is moving in this surface alone, its degree of freedom is only 2.
Yeah, fly. Then it's
If it can fly, it is 3. Okay. Same with gas molecule, it can move in X direction, Y and Z. There is a formula which relates this. Why are we confusing ourselves? We can make a formula which will help us to find the degree of freedom of any gas. What is that formula? Anybody knows? 3n minus? Yes. Degree of freedom is equal to 3n minus r. What is r here? Karthikeyan? Number of relations in simple language, technically it is called as redundancies. Number of redundancies or relation, local, our Indian English. Okay. Any kind of gas. Degree of freedom. N is number of atoms. N is number of atoms. Here I have only one atom. It has no relationship with any other atom. So R is 0. So what is degree of freedom? 3 into 1. How much is that? 3. Right? If I would have had a diatomic atom like this. Now pay attention. What is the number of atoms? 2. So 3 into 2. And what is the relationship between them? One relation is there between them. So minus 1. What is the answer? 5. So diatomic gas will have how much degree of freedom? 5 degree of freedom. If you have triatomic, there are two possibilities. One is this. It has two relations.
Rotational and translational.
Yeah, we'll talk about that. I'm talking now in simple way. First, I'm talking like if it is having two relation with them, then what is the degree of freedom? 2 into 3 is 6. Sorry, 3 into 3 is 9. Minus relation is 2. 9 minus 2 is how much? So degree of freedom is 7 for triatomic non-linear. Sorry, linear. If it becomes non-linear like this, 1, 2, 3. How many relations are there? 3 relation. So what is degree of freedom? 9 minus 3 is how much? 6. Which one? Last one or everything? Okay. Formula you understood? Formula is fine, right? We will explain how it is 5, but now how I am putting the formula understanding? No. Okay. So if it is a monatomic gas, how many atoms are there? One atom. So one atom will have no relation with any other atom. So I am taking R as 0. 3 into 1 is how much? Yes, this much time we took. Okay. If there are two atoms, how many relation is there between them? Relation means simple words. If I say in layman's language, how many lines are joining them? 1. So 3 into 2 is 6, minus 1 is 5. If I am keeping 3 gas atoms in a straight line, how many lines are required to join them? 2 lines required to join them. So 3 into 3 is 9, minus 2 is how much? 7. If I keep in non-linear way, then how many relations are there? These two will have a relation, these two will have a relation, this will have a relation. 3 relation. So how much? In layman's language. Okay. I'll go like how we sort of start speaking, but the translatory, vibrational, all these things. We'll talk about that also now. But first, layman's language is clear because you should not make a mistake in this. So degree of freedom, monatomic 3, diatomic 5, triatomic non-linear 6, triatomic linear 7. If you want to write this formula also, you can write those who are writing for the first time, and I'll tell you now in little technical way how it is. Shall I erase the board? Anybody has doubt in what I have written on the board? Degree of freedom, very basic thing I have done. Degree of freedom, how I have derived, anybody has any doubt in that? These things, very simple formula, 3n minus r, where n is the number of atoms, r is relations between them. A monatomic gas has no relation. A diatomic gas has one relation. Triatomic can have 2 relation if it is linear and 3 relation if it is non-linear. So based upon that, we can find degree of freedom of them, and we have got degree of freedom as different 3, 5, 6, and 7. Okay, I am erasing this. Shall I? Okay. So coming technically, so here, as you can see, this is clear. 3 directions it can move. So it has 3 degree of freedom. And what they have found, which is actually called as law of equipartition of energy. I'll tell you about that also. That's why they have written this value itself. So in the previous page, they talked about that. So I said in the beginning today, nature makes no discrimination. Nature says that for every gas, based upon its degree of freedom, we will allot the energy. So for example, if I go back and tell you, this is what a statement is. It states that for a dynamically system in thermal equilibrium, total energy is equally distributed in all possible energy modes. That is only called as degree of freedom. That is, how many degree of freedom is there? They will equally divide among all degree of freedom. So it's very simple to say, for a particular atom, what is degree of freedom? 3. So a particular atom has 3 degree of freedom. 3 degree of freedom. What is its energy? We have learned now. Its energy is 3 by 2 kT, isn't it? So 3 by 2 kT is for how many degree of freedom? 3 degree of freedom. So for each degree of freedom, how much is the energy? 1 by 3 times of this, which will become equal to 1 by 2 kT. Am I right? Yeah, E will become equal to 1 by 2 times of kT. Remember this, it's an important thing. 1 by 2 kT is the share of each degree of freedom. A gas has 3 degree of freedom. So what will be its energy? 3 by 2 kT. Obviously 3 by 2 kT for 3 degree of freedom. If a gas has 5 degree of freedom, how much energy it will have? 5 by 2 kT. If a gas has 6 degree of freedom, how much energy it will have? 3 kT. 7, 3.5 kT. Are you getting what I'm trying to say? Each degree of freedom will be allotted with 1 by 2, 0.5 kT of energy. Now, how much degree of freedom you have, that much energy you will get. Very simple. That's what nature says. That is what law of equipartition of energy itself says. Those who not wrote, please write the definition also. Those who not wrote, please write. It states that for a dynamical system in thermal equilibrium, total energy is equally distributed in all possible energy modes or all possible degree of freedom. In all possible degree of freedom. Total energy is equally distributed in all possible energy modes or all possible degree of freedoms. You can also write one more line after this, stating that for each degree of freedom, please write it down. I'm telling it verbally, not written here. Leave some line, man. I'm saying write that first. For each degree of freedom, the energy allocated as per law of equipartition of energy. The energy allocated as per law of equipartition of energy, as per law of equipartition of energy is 1 by 2 kT. Is 1 by 2 kT. kT means kV into T, Boltzmann constant into temperature. Yes, 1 by 2 kT. We not wrote the timer. Make it fast, man, please. Equally distributed in all possible energy modes. Distributed in all possible energy modes in bracket degree of freedom. So by that concept, here we have 3 degree of freedom for a monatomic gas. So for monatomic gas molecule, since degree of freedom is 3, the energy is how much? 3 by 2 kT. Simple. So in the same way, I hope you yourself can, they have found in terms of energy, that is multiplying with N. So that will become equal to 3 by 2 nRT. Because when you multiply kV with Na, then you get the value of R. So in that way they have written. So if you can even write this value. In terms of R, it is 3 by 2 nRT. Where N is the number of moles. Small is number of moles. Small n into R, if you multiply, you get kb. Yes, in that case we took number of moles as 1, so we wrote directly kb as R, remember? Otherwise, whenever you want to convert Boltzmann constant into gas constant, you have to multiply with number of moles. Remember this. Whenever you want to convert Boltzmann constant into gas constant, R is called gas constant, you have to multiply this gas constant with number of moles. Yes. So remember this, U is equal to 3 by 2 nRT. Okay. Same way, if I find for diatomic molecule, so diatomic molecule will have 5 degree of freedom. I told you by that concept. But what are those 5 degree of freedom? Obviously, it can have, I will draw and show you. The diagram will be there. Yes, see. Diatomic gas, no? One moving in x-axis. Another way it can move in y-axis. It can move in z-axis. Are you feeling how it is moving? It can rotate like this. It can even rotate like this. You may say third rotation is also possible. No, not possible, because it is there in one direction. No, in the same direction it cannot rotate. See, this particular gas molecule will be there in a particular direction. It can rotate only perpendicular to it. It cannot rotate in that direction. So there are 2 rotation possible and 3 translation possible. If you want to learn in detail, see, you can remember degree of freedom of diatomic gas is 5, 3 n minus r. But if you want to know how it is 5, this is the reason it is 5. See, this diatomic gas is there, no? It will be there in a particular direction, either x, y, or z. It can rotate. If I talk only about rotation, it can rotate only perpendicular to it. There are two more planes possible, because already it is in one plane. In which plane it is there, in that plane it will not rotate. I'll show you in the last slide. That will be written. See here. So diatomic molecule can rotate about any axis at right angles to its own axis. Hence, it has 2 degrees of freedom of rotational motion, and or in addition to that, 3 degrees of freedom of translatory motion. Are you getting my point? It has 3 translatory, 2 rotational, and that makes it 5 degrees of freedom. Examples also have given oxygen, nitrogen, and Cl2 and all these things. So degree of freedom of diatomic gas 5. If you don't want to learn this, no problem. Remember that it is 5, 3 n minus r. Okay. So they have written even the energies. Half mv square is kinetic energy. Rotational kinetic energy is half I omega square. This also you learned in rotational mechanics. Half I omega square, you remember or forgot? Rotational kinetic energy is half I omega square. I have taught this in the class. Yeah, directly, that same relation. M is I, V is omega. Yes, that way also you can remember. So half I omega square. Right. So for linear, triatomic linear, 7 we already derived, no? And for energy, 7 means 7 by 2 kT. Remember these things. For monatomic gas, 3 by 2 kT. For diatomic, 5 by 2 kT. For triatomic linear, 7 by 2 kT. And for triatomic non-linear, 6 by 2 kT. That is 3 kT. Same thing will happen. See here. Yes. Is it clear to you? How?
How does the 6 real rotates the 6 dimension? How does it rotate like that?
So read above.
I can't visualize it.
Read above, no, you will realize.
Non-linear molecule may rotate on the 3 mutually perpendicular axes. Therefore, it possesses 3 degrees of freedom
In rotation.
in rotation.
And in addition to the 3 degree of that
For
thing,
translation, I get it.
huh.
Rotation, I am slightly confused because diatomic, it has 2, sir. I can understand it. Same here, sir. It's not. Oh, it's non-linear.
Non-linear.
Okay, then I get it.
Are you getting? So this is how we have to find the degree of freedom and relate degree of freedom with internal energy. So there is U. So U is different for different degree of freedoms. Monatomic, I said you 3 by 2 kT, diatomic 5 by 2 kT, triatomic linear 7 by 2 kT, and triatomic non-linear 3 kT. Right? Then we have, yeah. Is it clear to everybody? All of you have made note to all these things? Any doubt up to here? No? Sure? Okay. Then we will go into specific heat of gas. I hope all of you have made note of all these things, whatever I have talked till now. Okay. I mean, I don't think yes, directly I'll enter into this. Okay. So now what we are going to do, we are going to find the specific heat of gas. Now specific heat are of 2 types, right? Specific heat of gases or fluids are of 2 types, which are specific heat at constant pressure and specific heat at constant volume. So what is Cp and what is Cv? Same thing you are going to say.
Yeah.
And the specific constant volume is Cv. How are they different from each other? And why is Cp more than Cv?
Oh, why is CP more than CV?
Yes. Cp is more than Cv. Are you aware about that?
Yeah, because minus that will give you gas constant.
Oh, since Cv minus Cv is giving you R, that's why it is bigger. If R is negative, R is
not
positive, we
negative,
know.
yeah. It's constant. It's
But
constant.
prove.
Sir,
Tell me.
heat supplied in CP is used to raise the temperature as well as the gas expands. Work is done, sir.
Hmm.
In CV, no work done, sir. Only temperature increases, sir.
Obviously.
So
Because the volume is
CV is less than CP.
Because in the case of constant volume, whatever energy you supply is going to use only for temperature increasing. Volume is going to remain
constant.
constant.
Oh,
So there is no energy required for changing the volume. Delta Q is equal to delta U plus P del V. Del V is 0 in the case of CV. So its value is smaller. Less heat itself will give the temperature. But in the case of CP, only pressure is constant. Volume will change. So whatever heat you supply will do two things. One thing, changing temperature. Another thing,
change in volume.
change in volume, P del V. So energy will be divided. So more energy is required to reach the same temperature. The same thing cycle is said now. So CP is always more than CV. Now in the case of gases, like if I am writing for monoatomic gas, what is the value of energy U, internal energy U? Just now we learned. How much is that? 3 by 2 kT. Right? So for a constant volume, for constant volume of gas, please pay attention. That is, I am taking V as constant. If V is constant, then what will be the value of CV? What is CP and what is C formula I am asking you? What is C formula? C is equal to
M by C
M by MC
delta T.
delta T.
Q by M delta T.
No.
Q is equal to MC delta T, isn't it?
Yes.
So what will be C? Q by M delta T. Yeah. So if it is moles, it is Q by
N delta T.
N delta T. Am I right? And what is Q for constant volume?
Constant volume.
Del Q is equal to del U plus del W, isn't it? Del W is 0 because volume is constant. So Q is equal to U. Del Q is equal to del U. If I want to write, right? If I want to write like del Q is equal to del U. Do you agree with me? So for 1 mole of gas, for 1 mole of gas, can I write CV as del U by del T? Can I write?
Yes.
Or I can write d by dt of U. And what is U? Del I am writing as differential d. So what is U for monatomic gas? 3 by 2 kBT. d by dt of T is 1. So what is CV? 3 by 2 kb. What will be CP then? Okay. Again. If I want to convert kb into R, what I told you, what we should do? No. kb, how will you continue to R? kb will become equal to n times of R, isn't it? And we have told just now that for 1 mole of gas. For 1 mole I can write kb is equal to R. So I am putting that here. So CV also can be written as 3 by 2 R. If CV is 3 by 2 R, what will be CP? Because CP is equal to CP minus CV is R. CP will become to R plus CV. So R plus 3 by 2 R. So CP will become equal to 5R by 5R by 2. So you have CP value, you have CV value. You can find gamma. Gamma is equal to CP by CV. What is CP? 5R by 2. What is CV? 3R by 2. 2 gets cancelled, R gets cancelled. What is 5 by 3? Yes, 1.67. How much is gamma? Check.
Yeah, it is 1.6. 1.6666. Vulgar fraction.
So gamma of a monoatomic gas is how much? 1.67. Very important for competitive examination, these things.
Sir, what's gamma?
Gamma is the ratio of CP by CV.
What is it known as?
I don't remember its name. It has some name, but remember it's the ratio of CP by CV. It's a constant. So it's
Adiabatic exponent, sir.
adiabatic
Exponent.
Actually, adiabatic constant also we say it. Correct, he's saying. Adiabatic constant. Or adiabatic exponent also we say it. So that is gamma. And gamma is Cp by Cv, where Cp value I told you how it has come, Cv how it has come, and then divide both, get 5 by 3. Same way, can you find gamma for all the gases? Take 5 minutes of time, do it fast. Yes. Diatomic, triatomic, linear, triatomic, non-linear. Simple. It will change for different gases. I have done in front of you for only monatomic gas. The same steps can you take and find the gamma value for all the gases? That is, what is the gamma for diatomic? What is the gamma of triatomic linear and triatomic non-linear? Do it fast.
Diatomic is 2, sir.
Then I'm not going to do it.
It's in my mind, sir.
Mind, don't trust your mind. Do it. Is it coming 2? Anybody has tried? For diatomic, it will become 5 by 2 kT, isn't it? So 5 by 2 R, and here it will be 7 by 2 R. So it will be 7 by 5, right? 7 by 5 is 2. Solve it, man. 7 by 5 is how much here?
1 by 5.
I think it will be 7 by 5. Check. All of you got 7 by 5?
1.4.
Yes, sir.
7 by 5. Okay. Then if it is triatomic linear, it is 7. Right. So 7 by 2 R and 9 by 2 R.
9 by 7.
9 by 7. What is that?
1.2 something.
1.2.
2.
6 will come.
8. 1.28. Yeah, 56, right? So
756. Yeah. 8. 1.2. Correct. What about non-linear?
non-linear.
Is 3. 3 RT plus R will become 4. 4 by 3. 4 by 3 is how much?
3 by 4 by 3.
1.33. Why I did this? Which gas has maximum gamma? Mono. Dia is 1.4. Mono is 1.67, right? And which gas has least gamma?
Now it's triatomic.
If you go to
What did he say?
what you said, Sai Akhilesh?
Triatomic linear, sir.
Yes, correct. Up to now, in this things, least gamma value is triatomic linear only. Got it? It's not that difficult thing if you're understanding. Some of you may be not known much to this formula, but if you know, it is very simple thing what I've done now. Some of you may not know what is CV minus CV is equal to R, but if you know, it is simple thing. So these things you should remember, right? So I'll wind off here today class. I'll have it. You can copy, man. I'm not going to erase it. But everybody, please practice how to find gamma. Don't leave it. I know some of you have not done now. What is the gamma of diatomic, triatomic, linear, non-linear? But do it by yourself. It is a practice for you. Find Cp, find Cv, find gamma. Right? So we have one topic remaining, mean free path of gas, and specific heat of water also is there in this chapter actually, which we will be discussing in the next session. Okay. So next class, when I come to meet you people, I am going to do 2 things. One is second law of thermodynamics. Small part is remaining, engine, and here small part is remaining. So next class, officially we will finish the whole syllabus, because waves oscillations already we have done beginning itself, and then this part. If you want some revision also, we will do after that. Okay. If you have some chapter requirement, you can ask me. I will do the chapter revision, or else I'll do the complete revision one by one myself. So let us wind up the class, and we will meet once again in the next class. Till then, take care. Bye bye. And people can drop off who are in online.
Thank you, sir.
Take care. Bye bye.
Yes, sir.
Bye bye, man. Bye bye. लाइट को बंद किया